G'day fellow flight simmers and random YouTubers. Today I'd like to talk about a subject which presents or is probably one of the hardest things to do in air traffic control, and that's sequencing using speed control. So today I'll talk about the tricks and some hints that may become useful in allowing you to safely apply speed control in your ATC endeavours. Okay, so the biggest challenge in the ATC environment is when you have this situation. You've got this slow aircraft, in this case the Dash 8, and he's on a 12-mile final, and you've got the 737-800 behind him who's doing 180 nautical miles. Now we can see from this scenario that based on each aircraft speed, both aircraft get to the runway threshold in roughly 6 minutes. And that's just using simple maths. You can see that ground speed of, and I won't go through the maths, but anyhow, it's quite easy. So how do we ensure that our 3 nautical mile, which is our standard in the TMA radar environment, how do we ensure that that doesn't break down? And having identified, knowing that there's a problem, at what distance should the faster aircraft be to ensure that we have at least can maintain our 3 nautical mile separation? So it's one thing to identify a problem, another thing is to alleviate it. So today I'm going to be going through some simple maths that I use to quickly work out a safe distance for the 737-800. Or any jet. It doesn't have to be the 737. Okay, before I get on to the maths, this is just a typical data tag, and the figure you can see on the right hand side, that's your ground speed. So when you're doing your calculations, you use that figure. So like I said, that's the ground speed of the aircraft indicated on the controller's radar. So the formula today that you really only have to remember is this formula here. And this formula applies only to the front aircraft, the slow, in our case, the Dash 8. And as you remember, or if you can remember, he had 12 nautical miles. It's a distance to fly over the speed. So you can see he had 12 nautical miles and he was doing 120 knots, but you don't use 120, you use 12. And you arrive at a figure, which is 1. So what does that 1 mean? That 1 indicates is the distance you need for every 10 knots of ground speed. Okay, so this is really the only thing you have to commit to memory. All the rest is just maths. So if you can remember that formula and apply it to the front aircraft, the rest hopefully will sort of fit into place. Okay, so let's go back to our situation. So what I'm going to do is there are 2 methods. Now the first method is calculating the faster aircraft's distance to the runway. Now as we said, or we previously worked out, we need 1 nautical mile for every 10 knots of ground speed. Okay, so the 737 behind is doing 180 knots. Therefore, he needs 18 nautical miles because, as we said, 180 divided by 10 equals 18. So he needs 18 nautical miles, but that's not where it ends. In addition to the 18 nautical miles, we have to add in our separation. In this case, 3 nautical miles. I personally use 4 nautical miles as a buffer. It just gives me that 1 nautical mile. You'd be surprised how much it makes a difference. So in total, that 737-800 or faster aircraft needs to be 22 nautical miles from the runway. Okay, to ensure that there's no breakdown in separation. So if he was 22 miles from the runway, we don't have to apply any speed restrictions. We can let both aircraft continue on. Okay, so let's look at method number 2. And this is relating to the faster aircraft's distance from the slower aircraft. So in this maths, we're going to work out what distance the 737-800 needs to be from the slower aircraft. So like I said, this time we look at the comparative speeds and the distance in the two aircraft speeds. And the difference, I should say, not the distance, the difference. Once again, you start with the dash 8 and you apply our formula. And once again, it's the same math. 12 over 12 is 1. So we get 1 nautical mile for every 10 knots of ground speed. However, we now look at their difference in speed and see how far away the faster aircraft needs to be from the slower aircraft rather than the runway. In this case, we have a difference of 6. In other words, 18 minus 12 is 6. Now, once again, like the previous example, to that figure, to 6, you have to add our separation. And as I said, I use 4. So you arrive at 10 nautical miles. That's the distance that the 737-800 has to be from the dash 8, not the runway. Okay, so they're the two ways, the mathematics. And if you look at it, if you look at the previous example, we said that the 737-800 had to be 22 nautical miles. Well, we worked out here that he has to be 10 nautical miles from the first aircraft. So if you add the 10 nautical miles plus the 12 nautical miles that the dash 8 is from the airfield, you arrive at the 22 nautical miles, which we used in method number 1. So both methods arrive at the same answer, but you do it in different ways. Okay, so let's look at a practical example. So it's no good me talking about all this theory if we don't actually find out how we can use it in practice. Okay, so most air traffic controllers would recognise this chart, and it's the RB arrival into runway 16 and also runway 09, but we're concentrating on 16 at Melbourne. Now, we can see the aircraft at Tunka is 8 nautical miles from the slow plane, the plane in red. And you can see, you just add up the distance from Tunka to Laysol is 5, and then from Laysol to Belter is 3. So we see he's 8 nautical miles from the slow plane. Now, I've actually set this up so we don't have to go through the calculation, but we saw from the previous calculation, we needed 10 nautical miles for adequate separation, because once again, you see this guy's 12 nautical miles out from, the first aircraft's 12 nautical miles out from the runway, because if you look at the ILS chart, you'll see that Belter is 12 nautical miles, doing 120, 12 over 12 is 1. And we looked at the blue aircraft, and he's doing 180 knots. And once again, we see that we need 1 nautical mile for 10 knots of ground speed. So we can see we needed 10 nautical miles for adequate separation. So having identified we have a problem, how do we remedy the situation? It's okay to know, we got a problem there, but how do we remedy? How do we sort of go about? And I've seen on the few hours that I've done observing, I'm seeing some controllers pluck numbers out of the old proverbial, and I'm thinking, you don't have to slow them down that much. So remember from when we said from our calculation that we need 1 nautical mile for every 10 knots of ground speed. Now, because the faster aircraft is 2 nautical miles too close, he's at 8 nautical miles, and we said we needed 10, we now have to reduce his speed by 20 knots, because once again, we go back to that same thing. For every 1 nautical miles, we need 10 knots of ground speed. If you remember that, we worked it out. So 12 over 12 is 1 nautical mile for every 10 knots. Now here you can see the blue aircraft is 2 nautical miles too close, so we need to reduce his speed by 20 knots. So basic phraseology would be to the blue aircraft, say velocity 239, reduce speed by 20 knots. So not only have we identified the problem, we've created a solution, and it's no good asking for indicated airspeed. By knowing that you could see the ground speed, by knowing that that's the speed that you have to reduce the second aircraft or the faster aircraft speed, you know that you've arrived at a reasonable solution. So that's that. That's in one particular example. So we'll look at another example, and this happens all the time. Once again, we can see there's an aircraft at Belt and he's only doing 120 knots, and we know he's 12 miles out, so I'm making the maths really easy. And we can see, now the question is, do we let the faster jet continue on his star? Because and most people would know this is the Warren arrival into runway 16. And I've seen the number of times I've seen guys continue the approach with the faster aircraft onto the slower aircraft. Okay, so as we worked out, we need 1 nautical mile for every 10 knots difference in their speed, because we worked out 12 over 12 is 1, and that's 1 nautical mile for every 10 knots. So we worked that out. Now the difference, in this situation, I'm using method number 2 to work out what distance the aircraft at NEFA needs to be from the guy at Belter. And you can see the difference in speed is 8, 20 minus 12, because the guy at NEFA is doing 200 knots, which is probably not unusual. So you see that we have 8. So we need 8 nautical miles, plus you have to add your separation of 4 nautical miles. So we need a total of 12 nautical miles that the second aircraft, the guy at NEFA, needs to be from the guy at Belter. As you quite rightly can see from the chart, he's only 7 nautical miles. Therefore, what we can do here is not necessarily reduce his speed, because you're going to be looking at trying to reduce his speed. If we go back, and for 1 nautical mile every 10 knots difference, you're going to be reducing his speed by 80 knots, which is ridiculous. So what you do here is you keep the faster aircraft on his present heading. In other words, you don't let him turn base, you don't let him continue on his star. In other words, you say to him, cancel, let's say the guy at NEFA is velocity 123, velocity 123, cancel star, continue present heading, or for sequencing, continue present heading. And then when you've got enough separation, and when the guy at Belt is close enough to his approach, then you can turn him onto base. But once you've got, so that would be another solution to that particular problem. Okay, so let's now look at example number 3. Now let's say, and this is probably, this is obvious, I think. Let's have a look at now, let's say our slow aircraft is on 6 nautical miles. Do we have adequate separation with the faster aircraft on his star? Now, you could probably guess what the answer is, but I just want to go through the maths. So let's just say, now we look at our first aircraft. He's 6 miles from the runway, and he's doing 120 knots, or 12. So we see that we need a half a nautical mile for every 10 knots difference in their speed. In other words, 6 divide the distance to fly over 12 gives you a fraction of a half. So we need a half a nautical mile for every 10 knots. Now the difference in their speed is 8. So what's half of 8? Is 4. Now we add in our 4 nautical mile separation for a total of 8 miles. Therefore, the guy at NEFA has to be 13 nautical miles from the first aircraft. In this case, we need the first aircraft, the guy at NEFA, to be only 8 nautical miles away from the guy on 6 mile final. Here we have 13, because you can see from NEFA to Belter 7 nautical miles, and then from Belter to the aircraft, the slow aircraft, another 6. So you can see here we can let the jet at NEFA continue his star. Okay, that's probably intuitive, but I just wanted to go through the maths there. So in that situation, we don't have to worry about reducing speed. We know that both aircraft can continue with their normal speed. Okay, now let's say we got this situation. We got the guy in red, he's doing a ground speed of 120, but instead of being 12 miles, he's now 9 miles. And the guy at Tunka, he's doing not 200 or 180. Let's just make it more realistic. He's doing 230. So what you do, and you go through and you look at the maths, and it can become quite onerous. So what you do is you make the math simple. So like I said, the Dash 8 is on the 9 mile final, and the faster jet is doing 230, and he's 11 nautical miles behind. You can see from Tunka to Leysol's 5, and then from Leysol to Belter's 3, that's 8, and then another further 3 miles from Belter to the aircraft, or to the red aircraft, because he's on a 9 mile final. 9 and 3 is 12, which is your distance from Belter to the runway. So assume we need, let's say we use method 1. So we look at the maths and we go, okay, let's do the maths. So this guy, the red guy, he's 9 miles distance to run. Over his speed is 12. We get 3/4. So now we say, well, what 3/4 of 23, which is what the speed of the guy in at Tunka, and you look and say, oh, well, God, what's 3/4? So the maths becomes quite hard. So instead of making the maths difficult, what you do is, instead of saying he's doing 230, say he's doing 240 knots or 24. So getting 3/4 of 24 is much easier than working out 3/4 of 23. And also by making your speed a little bit quicker, you're adding in more of a buffer. Now, for those of you who aren't mathematically inclined, working out 3/4 of a figure is easy. All you do is you get the figure, you halve it and halve it again. So in our case, let's say the guy at Tunka, we say he's doing 24, in other words, 249. Half of 24 is 12, half of 12 is 6. So 3/4 of 24 is 18. Okay? So that's a lot easier to work out than actually going through the precise maths. Okay, so, and you can see in this situation, we've got 8. So once again, we've got the problem here, and so we have to find out a way of fixing it. So, but this is, like I said, don't get embroiled in the maths. Try to make the maths easier. And the fractions I use are either, use whole numbers, or use quarter, half, or 3/4. Don't be looking at, the 2/5 or 7/8 or fractions like that. Try to look for making easier fractions so you can work it out in your head. All right, so I think that wraps it up. Whatever you do, don't let this be you. So anyhow, I hope I've provided some helpful hints. And if you like what I've got, don't forget to subscribe. Until next time, see you all later. Cheers.